I don't believe that there's a variety of ways to solve these problems. I think there's a way to solve these problems, and I'm not going to go over all the different other things you might be able to do. It is a statics problem, and whether you're in college doing this or you're in high school physics doing this, statics problems come down to three knowable things. First, for it to be a statics problem, the net force has to be equal to 0. Again, these are statics problems. The net torque has to be equal to 0. But this isn't enough. Statics also means velocity equals 0. You need to be careful here. Static problems, the system's not moving. A net force equals 0 problem, the system could be moving, it's not accelerating. A net torque equals 0 problem, the system could be moving, it could just not be accelerating. But a statics problem, we're going to assume velocity is equal to 0. I generally like to start by creating a picture that models the forces acting on the system in such a way as to give us an idea of their distribution in the problem. So I'm going to make a representation of the meter stick, and then I want to walk through and kind of draw arrows to indicate each of the forces that acts on the object. For example, I know we have 2 upwards forces that act on the object. I'm going to say T20 and T80. Pretty okay with that? All right. In addition to that, we have mg for the mass that is hung. So this ends up being 0.5 times, I'm going to go ahead and just use 10. I know that that's not going to be reflected in the meters, actual numerical answers, but for us to work this out, that'll be easy. And at the middle of the ruler, I've got 0.07 times 10. Yeah. Am I okay? Yeah, this is the weight of the meter stick, and this is the weight that I hung on there, the 500-gram mass. Is that okay? All right. Now, if you're taking notes and you want to do more than just, like I joked about in the beginning of class, more than just, write down what I write down, notice the things that I did that you should probably replicate. I drew something to represent the object. I put the forces as they appear on the object. I've not really given us enough information. We could go further, and you could start saying, well, this is at the 20 centimeter mark. I'm purposely not doing that because of what's going to come next, but you may want to. It just starts adding more distraction to your diagram. But you need to, I think, idealize on your diagram where the forces are acting relative to each other, just to get a start. And also, I'm trying to give us an idea of the direction the forces act relative to the object itself. They're all acting up and down, and I tried very diligently to make sure my object was level. That's to help me identify the direction that these forces act. Because if you'll recall, torque involves 3 principal parts. And you guys know how I like making those charts that have, principal parts. We fill out the 3 buckets of information, trying to give you a little bit of scaffolding to hang these ideas on. Now, I started this whole discussion indicating that we need to look at both torque and force, because if we look at just force, which we're going to do first, net force equals 0. There are 4 forces. There's T80, and I'm naming it that because it's at the 80 centimeter mark. Don't think too deeply about it. It's upward, so I'm making it positive. There's T20, again, upwards, making it positive. There's negative 0.07 times 10 mg for the meter stick. And there's negative 0.5 times 10 mg for the weight hung on the meter stick. That has to equal 0. Now, I'm going to do something a little drastic today. We can't solve this for either one of those forces. That's the whole point. Net force isn't enough. So we're going to use net torque. We know that if the torques aren't balanced, the system rotates. We've seen the conditions that it could be set up to rotate, so we know we have a net torque problem here. The problem with the net torque problem in this case is it's not actually rotating. We know that 3 conditions are required for us to be able to calculate torque, but where's the pivot point? Right? If it's not actually rotating, is there a clear pivot point? We know we can force it to pivot about one point. We did that, right? That was my example. But the real question is, what should I use as a pivot point? I'm going to tell you that the best way to deal with this problem is to understand something unique to statics questions. There is no pivot. So any place can be a pivot point. In a statics problem, you get to choose where to put the pivot point because the system isn't actually pivoting. Now, there might be times where you are forced to pick a place that's specific to the problem. But in most cases, if the system is not accelerating, the torques are balanced, so any place can be your pivot. Now, hear me out. If any place can be your pivot, you choose a pivot point that's most convenient to you. You want my opinion? You put the pivot point at an unknown. Look, in this problem, there are 2 unknowns. If I place my pivot point here at the T20 spot, if I place my pivot point there, then the distance from the pivot point to T20 is 0. That eliminates T20 from the equation. You can pick any place you want, as long as it's the same for all the torques. So pick a pivot point that eliminates one of your unknowns. Now, you don't have to do it that way. But if you don't, then you have a 2 equation and 2 unknown problem that you have to do simultaneous solution for. So if you pick a place that eliminates an unknown, you don't. So I'm going to choose a pivot point, and my choice is going to be right here. I'm going to choose the T20. I get to pick any place I want. That's where I'm picking. Now, sliding this over a little bit to give me a little bit of space. I am aware that there are 4 potential torques. I'm labeling them by their location or by the mass that's there. So T20 and T80 are the torques at the 20 and 80 centimeter mark. A T70 is the mass of the meter stick, and T500 is the mass that's hung. And I'm listing them like this because, as you know, whenever I have something that has like buckets like this, I always like to kind of help you find a way to be organized. You don't have to do it this way. I never did it like this in high school or in college. I never did this in high school. But I want you to have a way to organize. We know we have to add all these together and they have to equal 0. I'm trying to help you organize because some of you need it. This does not come intuitively to you. So we're going to start at T20. And looking at my picture, what is the distance from T20 to the tension that acts at 20? 0. That one's easy. So, I could write the rest. This is T20. Sign of the angle is a little bit ambiguous, but it doesn't matter, does it? Right? It doesn't matter. There's no torque arm, so there's no torque provided at that point. If the force is at the pivot point, it does not apply a torque. So let's go to the next one, 80. What is the distance from 20 to 80? So 0.6. I have to put things in meters because I'm using G, and G is in meters per second squared, so I'm going to put everything in meters. The size of that tension is unknown, so I list T80. And what is the angle between the tension and the torque arm? Well, what's this angle? 90, right? Yeah, 90. So 90 degrees. We're going to handle the direction of the torques at the end. So I'm going to go on to the next one if that's okay. the net torque is the torque from the 500-gram mass. So what is this distance? Excuse me. So that goes from 20 to 40. So what is it? 0.2. Yeah, 20 to 40 is 0.2. When converted to meters. What is the size of this force? Well, it's 0.5 kilograms times 10. And what is the angle between that weight and the torque arm?
Negative 270.
I know there's a desire to do that. We're not going to do that. And look, I'm not trying to fool you here. You could say 270, but be careful when you do so. Phi was supposed to be the angle between the applied force and the torque arm. And you should use the most acute angle there that you can. So it's going to be 90. We'll determine direction later. If you don't do it this way, and you use 270, sine of 270 is -1. Be careful. Understand what that negative means. You following me? I choose to do positive and negative by using the right-hand rule. I would encourage you to do so as well. I know you're using the unit circle, and I am not working against you there. But use the most direct angle here. I think you'll understand why. If you don't, you're going to get negative signs, and then you have to figure out why. Yes, ma'am?
Should the distance be 23? Because the 70 is up to the 50 centimeters.
But we didn't do the 70. We're doing the 500. I wrote it in the wrong spot. This is 40, right? Fine. And I must be writing in the torque equals 70 spot, is what you're saying to me. Yep, okay, good. Yes, Mr. Shelton, you screwed up. Okay. I can take it. I can take it. So yeah, this will not be 0.2, this would be 0.3. That's not 0.5 then, that is 0.07. So we are not talking about the hanging 500 mass, we are talking about the weight of the meter stick. Sorry, everybody. And viewers watching at home, bummer. I told you shouldn't watch my videos, they're terrible. So
You have 449 subscribers now? It went up.
So excited. More people can watch my crappy videos. Sine 90 still okay for this one? Weights downwards, perpendicular to the torque arm? Alrighty, well, since I did all the work for that one, I'm just going to speed through this one because that's all got to be the same, and yeah, still sine of 90. Yay! Okay. So now, I think it's appropriate that we go through and deal with direction. Right-hand rule. Now look, I'm not trying to make this hard. Right-hand rule. But at the same time, just look at this force and this pivot point. Can't we all agree it's got to go that way? If that were the only two things acting, wouldn't it go that way? I mean, how about this one? If that was it and that's the pivot point, wouldn't it have to go this way? It'd have to. And if this is the pivot point and you're pulling that way on it, wouldn't it have to rotate that way? I mean, there is that. And I could use that idea alone and say clockwise and counterclockwise. I'm making it extra hard by using the right-hand rule. But technically, out of the board is supposed to be positive and into the board is supposed to be negative. So let's identify that so we're doing it correctly. I'm going to start not with this one. I'm going to start with that one, the T80. So starting at the pivot point, right hand. Pointer finger points in the direction of the torque arm. That is from the pivot point to where the force is. And then I rotate my wrist until my middle finger points in the direction of that force while leaving my pointer finger directed in the direction of the torque arm. My thumb goes into the board. This torque must cause the system to rotate this way. That is a negative torque. So I'm going to put negative in front of that torque. Negative in front of that torque. Moving on to the center of mass of the meter stick. R points this way to the center of mass. So point my pointer finger this way. Rotate my wrist until my middle finger points in the direction of that force. That's downwards. My thumb points out of the board. That means this torque is this direction, out of the board. That is a positive torque. Positive torque. I am positive. That's a torque. Last one. Pointer finger points this way. I rotate my wrist until my middle finger points in the direction of that weight. I notice that my thumb points out of the board. This is a positive torque. It must cause it to go this way. Boom. All right. I've assessed positive and negative for each torque. I've identified all 4 torques that act on the system. My job now is to sum all the torques and set them equal to 0. So I will do that. I have 0.6 times T80 times the sine of 90. That's negative 0.6 T80. Next torque, plus 0.3 times 0.07 is 0.21 times 10, 2.1. 2.1 sine 90. That is wrong. 0.21. 0.21 sine of 90. I'm not even going to put the sine of 90 because that's 1. 0.21. That good? I mathy math okay? Yay. Way to mathy math. Moving on. 0.2 times 0.5 is 0.01 times 10 is 0.2 times point. It's all 1. That's just 1. I can do that math. 1. There. 1. Equals 0. Yay. So I'm thinking 0.6 T80 equals 1.21. So the tension at the 80 centimeter mark has got to be about 2 newtons. Right? 1.2 divided by 0.6. That gives me one of my answers. It does not give me both of my answers, by the way. It just gives me one. But I have a way of getting the other answer. Now, if we had chosen a different pivot point, we still would have been able to get the answer, but we would have had 2 equations and 2 unknowns and would have had to do substitution. We're still doing substitution, but this is far easier because it gets us one of our answers right away. But now I have 2 newtons plus T20. 10 times 0.07 is 0.7. 10 times 0.5 is 5. Did I do that right? Yes. Equals 0. So that's, wait, these are both negative. Sorry. So let's see. I don't need the n on the 2 for the newtons, though. That's just distracting, so let's get rid of that and see if we can solve for T20. That's going to be 5.7 minus 2. That looks like T20 is 3.7 newtons. Now, what? Does that fit into our schema? Is one of the tensions greater than the other? Is it the expected one? Is it the one where there's more mass closer to it? All that seems pretty expected. Are we going to get those 2 answers when we set this up? Probably not. The meter itself is going to have some error in it, and we didn't use 9.8. But I bet we get a similar ratio. Let's try. Let's try. So to do that, I need to connect to the sensors. I'm going to try that. Let's see if this will work. There we go. That's a lot of email I got to go deal with. Proximity connect. All right, let's turn these suckers on. Sorry, right in front of you. All right, there they are. Connect 1. the other. All right, we want the meters. All right, so it says one of them is 3.88 and one's 2.43. Not bad, not great. Part of the reason I think we got some problems is not the reason you think. Are they zero now? No, the meters have, unfortunately, some play in them, and they have been zeroed out. And I don't have time to do that because we're at the end of the class period. So they are certainly off, and we'll have to zero them out. But with 1 minute remaining, it's difficult. It's faster for me not to change projectors, which is why I didn't. But I think we could play around with this a little bit. We'll get some decent data. We're going to look at a couple of situations like this, do some practice, and then we're going to start looking at something more complicated. We're going to go on to like boom arms, stuff like that tomorrow. But do we get the general principle here? I went very slow and deliberate. It was on purpose. I want us to get this the first time. So I'm hopeful.